Hey, AP Physics 1 students. Sorry I couldn't be there in person today, but I'm going to record a little video here walking you through a problem that will help you do the homework. So I'm working in the packet here off of the page that says Newton's second law example, and let's see what we have here. So the problem says that Bob has a mass of 50 kilograms and sits on a 20 kilogram desk. All right, I'm just going to get an idea of what's happening here. So here's the desk. I'll call that D. Here's Bob. I'll call that object B. And Alice, another character, Alice, pushes the desk to the right with a 200 Newton force. That's Alice pushing the desk to the right. We're told that the floor exerts a kinetic frictional force of 60 newtons on the desk, and everything moves to the right. So everything has a velocity to the right and has the same acceleration. I guess everything's accelerating to the right as well. All right, the first thing we want to do is draw three free body diagrams, one for each of the objects. Now, when I draw these free body diagrams, I'm going to um, draw them kind of in the same positioning as they appear in the little picture up here, but I'm going to give some space between them so all the force vectors are easy to identify. So there's the desk, and the desk has a mass of 20 kilograms. So like mass desk equals 20 kg. All right, Alice is somewhere over here. Yes, she's pushing on the desk, but to draw her free body diagram, I don't want the vectors for the forces on the two objects to overlap. So Alice has a 30 kilogram mass. So MA, the mass of Alice, is 30 kilograms. And here is Bob, who is sitting on the desk, but I'll draw Bob up here. And the mass of Bob is 50 kilograms. All right, and so now we can start drawing the forces on the three different objects. Well, each object has a gravitational force exerted on it by the Earth. So FGA is the force of gravity on Alice. FGD will be the force of gravity on the desk. And FGB will be the force of gravity on Bob. So beyond that, let's choose objects. Let's choose one object to draw the free body diagram for. Let's start with Bob. So Bob is sitting on top of the desk. There's the gravitational force from the Earth pulling him down. And I know there must be a normal force from the desk pushing Bob up. I'll call that FNB for the normal force on Bob. All right. Now, are there any other forces on Bob? Remember, everything is accelerating, moving to the right and accelerating. So if everything's accelerating to the right, Bob must be accelerating to the right. There must be some net force on Bob directed to the right. And the only force capable of pushing Bob to the right is a force that the desk exerts on Bob in this direction. This is what I'm going to call FSB, the force of static friction acting on Bob. If there were no friction, then when the desk is, here's Bob up here, if there were no static friction, then when the desk moves to the right, Bob would just get left behind and plop down while the desk zips ahead. So the fact that Bob is getting dragged along and pushed along with the desk is because the desk is not letting Bob slip leftward relative to it. The desk is pushing Bob to the right with a static frictional force. And that's it. Those are the only forces acting on Bob. And I can see that Bob will accelerate to the right because of the force of static friction that's unopposed, pushing him to the right. Now, how about the desk? So there's a force of gravity down on the desk. There's also a normal force down on the desk. That's right, down. There's a normal force pushing the desk down because Bob is sitting on top of the desk. There's another way to look at that. If the desk pushes Bob up with a normal force, then Bob must push the desk down with a normal force. That's a Newton's third law pair across these two free body diagrams. I'm going to label that normal force FNB, because it is the same value normal force strength-wise that the desk exerts on Bob, but this is just the Newton's third law counterpart to that force. So the Earth pulls the desk down, Bob's pants push the desk down with a normal force, and of course the ground pushes the desk up. I'll call this FND for the normal force on the desk exerted by the ground. What else? Well, we know that Alice pushes the desk to the right. So there's this, I'll call it a contact force from Alice pushing the desk to the right. And we know the value of that force. We're told in the problem it's 200 newtons. We're also told that as the desk slides rightward, there's a force of kinetic friction on the desk equal to 60 newtons. 60 newtons. All right, is there anything else? Well, once again, we can think about Newton's third law. If the desk is exerting a static frictional force to the right on Bob, Bob must be exerting a static frictional force to the left on the desk, which I will call F static B, because again, it's the Newton's third law counterpart to a force we previously identified. And that's it. The desk's free body diagram is pretty complicated. Gravity pulls down, the ground pushes up, Bob's pants pull down, Alice's pushes to the right, Alice pushes the desk to the right. As it slides, kinetic friction pushes to the left, and just as the desk pushes Bob to the right with a static frictional force, Bob is limiting how quickly the desk itself can slide by exerting a static frictional force to the left. Okay, Alice has a normal force acting on her, F normal Alice. The Newton's third law counterpart to the contact force that Alice applies to the desk is an equal and opposite contact force of 200 newtons that the desk exerts on Alice. And finally, it looks like Alice is going to accelerate to the left right now, that the net force on Alice is to the left, but that can't be. Alice is accelerating to the right along with everything else. So there is a force of static friction, which I'll call FSA. That's the force of static friction acting on Alice's feet. And I'll zoom in on this just a bit so that you can see this a little better. Okay, so Alice is being pulled down by gravity, pushed up by the normal force, pushed leftward by the desk, but pushed rightward by the floor via static friction. And I think it would benefit you to, look at these diagrams that I produced here. I identified some of the forces based on the fact that Newton's third law pairs of forces exist between these three objects, between pairs of these three objects. And that kind of helped me complete the free body diagrams. All right, next, we have question 2, where we're told to determine the strength of each force. Well, I already know 2 forces. I know that the contact force on the desk from Alice and the contact force on Alice on the desk is 200 newtons. And I also know that the kinetic frictional force that the floor exerts on the desk is 60 newtons. Everything else I have to calculate. The gravitational forces are the easiest forces to calculate next, right? The gravitational force on an object is the mass of the object times the Earth's gravitational field value. The AP test allows you to use an approximation of the Earth's gravitational field. Instead of saying 9.8 newtons per kilogram, it lets you use 10 newtons per kilogram. And I'm going to do that to simplify the calculations as well. So for instance, the gravitational force on the desk is equal to the mass of the desk times the Earth's gravitational field. The desk has a mass of 20 kilograms. The Earth's gravitational field is 10 newtons per kilogram. And so the desk has a gravitational force pulling on it, which we call the desk's weight of 200 newtons. So let's fill these values in. The gravitational force on the desk is 200 newtons. Alice has a 30 kilogram mass. If I multiply that by 10 newtons per kilogram, I find that Alice's weight, the force of gravity on Alice, is 300 newtons. And for Bob, with the 50 kilogram mass, his weight is 500 newtons. Next, we can look at the normal forces. Bob doesn't accelerate up or down. Bob's velocity in the y direction, like every object's velocity in the y direction in this problem, is 0 and it remains 0. So there's no acceleration in the y direction for any object here, and so there's no net force in the y direction on any object. Therefore, if a 500 Newton gravitational force pulls Bob down, a 500 Newton normal force must push Bob up. Alice must have a 300 Newton normal force pushing her up. And now we have to be a little careful. It would be a mistake to say that because gravity is pulling the desk down with a 200 Newton force, that the normal force up on the desk is also 200 newtons. That's because there's another force pushing the desk down as well. The desk exerts a 500 Newton upward normal force on Bob, so Bob is exerting a 500 Newton normal force down on the desk. Therefore, there's two things pushing the desk down: 200 newtons of gravity, 500 Newton normal force from Bob's pants, and the total force that the ground exerts on the desk is 700 newtons of force. The ground would only push up on the desk with a force equal to the desk's weight if nothing was sitting on top of the desk. But because something is, the ground has to push up harder than usual. All right, let's take stock at what we have over here. So there's a few forces we don't know. I still don't know the force of static friction that the desk exerts on Bob. And the force of static friction that Bob exerts on the desk, the numerical values will be the same, but I don't know what that value is. Furthermore, I don't know what the force of static friction is on Alice's feet. So there are two forces to find: the static frictional force between Bob and the desk, and the static frictional force that the ground exerts on Alice's feet. Now, based on things that we've discussed already, we're really at a dead end here. We don't know how to find these things. So this is where a new technique comes into play. It's the idea of identifying a system that you then apply Newton's second law to. And I'll tell you what I mean by that. If two or more objects have the same velocity and acceleration, meaning they move as a single unit, you can group them into a system. Anytime two objects have the same velocity and acceleration, it means they're moving kind of as one. And therefore, you can treat them as a single object. For instance, I'm treating each leg of the desk as well as the top horizontal surface of the desk. Those are three things I mentioned. Like, well, there's probably four legs. So the desk has four legs and one horizontal surface on top. So there were like 5 things there, but I group them together and just call them the desk because they're all rigidly connected to each other and they don't move independently of each other. So how does this help us? Well, let's group Bob and the desk together. Okay, let's group Bob and the desk together. Here's the desk. Here's Bob on top of the desk. And I'm going to draw a little bubble around them. Inside the bubble is the Bob plus desk system. And if I can find the acceleration of the Bob and desk system, well, then I know what the acceleration of Bob and the desk separately are. It's the same value as that for the system. And that's also going to be the acceleration value for Alice. And I'm actually able to do this because even though there are forces in the individual free body diagrams that I don't know, I know all the values of the forces acting on the Bob desk system. The force of gravity on the Bob desk system is just the combined forces of gravity on Bob and the desk, which are 700 newtons. The normal force on the Bob desk system is similarly 700 newtons. And recall that 700 newtons actually is the force being exerted upward on the desk by the ground. It's also the normal force on the Bob plus desk system. We have Alice exerting a contact force on the Bob desk system of 200 newtons. And we have a force of kinetic friction equal to 60 newtons from the ground. Now, I do not know what the static frictional forces are between Bob and the desk, but I don't care about that. Grouping them as a system means the details of what's going on in there doesn't matter. Now we can apply Newton's second law to the Bob desk system. In order to indicate that that's what I'm doing, the mass that I'm going to write here is the mass of Bob plus the mass of the desk. This is how I show you this is how I will show, and I expect you to show me what object, or in this case, what system of objects you're applying Newton's second law to. Okay, the net force on the Bob desk system is the magnitude of the rightward contact force minus the magnitude of the leftward kinetic frictional force. That is 200 newtons minus 60 newtons equals, Bob and the desk collectively have a 70 kilogram mass. And so I have 140 newtons equals 70 kilograms times the acceleration. It looks like the Bob desk system accelerates at a rate of 2 meters per second squared, picking up 2 meters per second of speed every second in this case. Great. So now I can go back up here, and I know that Bob is accelerating to the right at 2 meters per second squared. Well, what if I apply Newton's second law in the x direction to just Bob now? Well, in the x direction, there's only one force acting on Bob. It's a positive force of static friction that the desk exerts on Bob. And I don't know its value, but I do know that Bob's mass is 50 kilograms. And Bob is accelerating, I just found, at 2 meters per second squared to the right. 50 times 2 is 100 newtons. Therefore, it is a 100 Newton static frictional force pushing Bob to the right. Think about that. F net equals MA. So Bob has a 50 kilogram M, a 50 kilogram mass, has an acceleration value of 2 meters per second squared. And that tells me the net force on Bob is 50 times 2 is 100 newtons to the right. As there is only one horizontal force on Bob, that must be 100 newtons. We can turn to, well, actually, we know another value now. We know that the static frictional force that Bob exerts on the desk is 100 newtons. And now we can turn to the last force over here that we need to find, the rightward static frictional force exerted on Alice's feet. Well, let's do a calculation. The net force in the x direction on Alice is the mass of Alice times her acceleration. The net force on Alice is what we want to find, the static frictional force on Alice's feet minus the contact force that the desk exerts leftward on Alice. So I want to find the static frictional force on Alice's feet, but I have to subtract on the left-hand side the contact force. And this equals Alice's 30 kilogram mass times her 2 meter per second squared acceleration. Looks like the right side is 60. So the static frictional force minus 200 equals 60. And so the static frictional force on her feet is 260 newtons. 260 newtons. Let's focus in on these numerical values a bit more. Okay. Whoops, sorry about that. What is going on? Okay. So Alice has a 30 kilogram mass. She's accelerating forward at 2 meters per second squared. 30 times 2 is 60. There must be a 60 Newton net force on Alice to the right. And there is. That 60 Newton net force on Alice is this 260 Newton net force minus this 200 Newton net force. That gives me the 60 Newton net force to the right that accounts for Alice's acceleration. Now, I encourage you to look at the forces on the desk. There's a 200 Newton force to the right, a 60 Newton force to the left, and a 100 Newton static frictional force to the left. Take a moment and figure out what the net force on the desk is. Okay, so it's 200 to the right minus a total of 160 to the left. That's a net force on the desk of 40 newtons to the right. So the desk is being pushed to the right with a net force of 40 newtons. Dividing by the mass of 20 kilograms, I get that magic number, 2 meters per second squared, which goes to show that our analysis here is totally consistent and the desk does exactly what we would predict it to do. Okay, in the homework assignment, I'm having trouble zooming out. There we go. In the homework assignment, there probably will come a moment where it benefits you to do this sort of thing, to group two objects that move as a unit together, find the acceleration of those two objects, and then kind of dig inside the system and say, well, each piece of the system has this acceleration value I just found. What must be the value of other particular forces acting on the system to make that so? You're now well equipped to attempt this, and we'll see how you did when I see you all next week. Have a great one.